Today, we're jumping right into something pretty mind-bending. It's a concept that Albert Einstein famously called, spooky action at a distance. Quantum entanglement. And a really wild part. What he found so bizarre, so counterintuitive, well, it's now right at the heart of this revolutionary new field. Quantum machine learning. Yeah, it's where quantum computing principles meet. Classical AI. So our mission here is to really pull back the curtain on how entanglement, this uniquely quantum thing, isn't just driving QML forward. But, maybe surprisingly, it's also throwing up some of its biggest roadblocks. This deep dive is for you, whether you're, say, prepping for a meeting, trying to get up to speed on a field that's moving super fast, or maybe you're just really curious about what's next in computing. We want to give you the clearest insights, maybe some surprising facts, but without drowning you in jargon. Because really at its core, this whole topic shows this kind of profound duality. Entanglement is the secret sauce, right?
It's the key resource giving us access to computational power we couldn't even imagine before. But, and this is the twist we'll get into, if you don't handle it just right, too much of this powerful ingredient can lead to these things called Barren plateaus. And that can make these super sophisticated quantum models, well, completely untrainable. It's a fascinating paradox. So, okay, let's unpack that. How does entanglement, this weird quantum correlation, actually become a computational resource?
Yeah, that's really the perfect place to start because entanglement, it fundamentally changes how we even think about information processing. At its most basic, it means two or more particles get so deeply connected, so intertwined, that you just can't describe their quantum states separately anymore. Instead, they share one single unified quantum state, even if they're miles apart. This leads to what people call unbreakable correlation.
Unbreakable correlation, so like they're permanently linked.
In a quantum sense, yeah. Think about regular coins, heads or tails, each is independent. But with entangled qubits, maybe in something like a Bell state, they're so linked you have to describe them together. It's one identity, almost. That's this non-separability idea. It's where the power comes from. Now, Einstein, Podolsky, and Rosen, back in 1935, they really questioned this. That's where spooky action at a distance came from. But then John Stuart Bell's work in the 60s and experiments in the 70s and onwards, they really proved these non-local correlations are real. They just don't fit classical physics. And importantly, this doesn't mean faster than light communication. You still need classical communication to make sense of the measurements.
Okay, so it's not just that they're linked, but they form this kind of indivisible unit. And that unbreakable connection lets us process information in totally new ways, ways a classical computer just can't touch. Is that the Hilbert space advantage idea?
Precisely. That indivisible unit concept is absolutely key. Classically, n bits give you one of 2n possible states at a time. But qubits, thanks to superposition being 0 and 1 at once, n qubits can explore superposition of all 2n states simultaneously, this huge state space. That's the 2n-dimensional Hilbert space. Think of it as like the ultimate quantum playground.
A playground where all possibilities exist at once.
Exactly. But here's the crucial part. Superposition opens the door to the playground, but it's entanglement that lets you create the really rich, complex, useful correlations inside that playground. Without entanglement, n qubits are just, well, n separate qubits, but when they're entangled, they act as one unified system, described by this exponentially large set of numbers, these complex amplitudes, that exponential descriptive power. That's what QML algorithms grab onto. They use quantum feature mapping, often involving entangling gates to encode classical data into these really complex, entangled quantum states. And it's that structure that lets the QML model spot intricate nonlinear patterns that classical methods would likely miss.
That exponential growth. It still sounds kind of mind-bending. Is it just about the sheer size, or is there something fundamentally different in how information is used in that quantum space?
That's a great question, and it gets us to something really deep. The quantum no free lunch theorem. You know, the classical NFL theorem says no single algorithm is best for everything, and you're always limited by your data.
Right. More data usually means better results.
Well, people wondered if QML would hit the same data wall. But some fascinating research out of Los Alamos showed something cool. By deliberately entangling your quantum data set with an external reference system, you can effectively trade entanglement for data.
Trade entanglement for data, meaning you might need less data.
Potentially, yes. For certain tasks, the entanglement introduces correlations that a classical model just can't see, possibly reducing the need for massive data sets.
Wow. So the aha moment isn't just speed, it's changing the data game itself. Like having a special lens to see patterns in a small sample that you'd otherwise need tons of data for.
Exactly. Though there's a subtlety, this dual effect. More input entanglement can mean less error or less data needed. But if your measurements are limited, which they often are in quantum systems, actually getting all that rich information out is hard. You might need more powerful measurements, maybe even entangled measurements, to really leverage it. So the advantage shifts sometimes from pure speed up to, say, sample complexity, getting more from less data, but needing clever ways to extract it.
That's incredibly powerful stuff. So entanglement isn't just some weird quantum quirk. It's like a computational currency. It buys us access to these huge spaces and might even cut down our reliance on big data.
It absolutely is a currency, and what's really compelling now is seeing how algorithms actually spend that currency. It's not just theory, it leads to concrete algorithmic approaches, each using entanglement in its own clever way.
Okay, so let's get into that. How are QML algorithms actually putting entanglement to work? What are some of these paradigms?
Well, we can look at a few key types. First up, maybe quantum kernel methods like the quantum support vector machine or QSVM. Classical SVMs use a kernel trick to find patterns in high dimensions.
Right, mapping data to find separation.
In QSVM, you replace that classical kernel with a quantum one computed on a quantum computer. You encode data using a quantum feature map, and critically, this map uses entangling jates, like CNOT or CZ. The quantum computer estimates the similarity, the inner product between these entangled states. That becomes your kernel matrix for a classical SVM, the win. Entanglement lets this quantum kernel capture really complex, nonlinear correlations that classical kernels just can't handle efficiently.
And this actually works in practice.
Yeah, we're seeing real results. One study on tricky respiratory data showed a QSVM with an entanglement-boosted kernel got like 45% higher accuracy. And in finance, people have seen QSVMs beat classical models like random forests on speed, lower latency, faster inference.
Okay, that's QSVM. What else?
Then there are variational quantum circuits, or VQCs. You often hear them called quantum neural networks, QNNs. These are usually hybrid quantum classical. There's a quantum circuit with adjustable parameters, the ansatz, which is like our quantum model template.
Right, the part that runs on the quantum chip.
Exactly. And a classical computer runs an optimization loop tweaking those parameters. Here, entanglement isn't just for input. It's a core, trainable part of the model. The entangling gates, they're like the synapses in a brain, creating correlations between qubits. They define the model's expressivity, its ability to represent complex functions. More depth, more entangling layers, generally means exploring more of that huge Hilbert space. In this NISQ era, the noisy intermediate scale quantum time wherein people design hardware-efficient ansatz and how the qubits are connected by entangling gates, the topology really matters. Linear, ring, all-to-all, it affects performance.
So with VQCs, we're actively tuning the entanglement, like tuning the connections in a neural net to learn patterns. That's neat. Are there other, maybe more specialized ways?
Definitely. We see entanglement-assisted classifiers and networks, too. For instance, there's a neat technique for distance-based classification. You entangle a Hilbert qubit with your data vectors. The amount of entanglement ends up relating directly to how different, how distinguishable those vectors are. And the cool part is, this can offer a quantum speedup that doesn't depend on how many dimensions your vectors have. We've seen this demonstrated experimentally, too.
Okay.
And then there's a more complex idea called Sunny-Lane supervised learning assisted by an entangled sensor network. It's a hybrid setup where a VQC actually generates a custom-made multipartite entangled state.
Multipartite, meaning involving many particles.
Exactly. And this state is distributed across quantum sensors. The shared entanglement helps reduce noise and allows for much lower error rates in classification compared to classical sensors. It's been shown to work for things like radio frequency signals, and it's even bleeding into classical AI. Some research is putting entanglement-based attention layers into transformer models, showing they can outperform standard attention, especially when data is scarce.
Fascinating. And what about optimization problems? Does entanglement play a role there?
Oh, absolutely. Entanglement is crucial in quantum optimization algorithms. Take QAOA, the quantum approximate optimization algorithm. It's used for hard problems like max cut. Its power comes from the entangling nature of its problem unitary, the part that explores the solution space. This generates deep, complex entanglement, sometimes called a volume law entanglement barrier, which is key to how it explores solutions in a way classical algorithms can't.
So the entanglement is fundamental to how it searches.
Yes, and similarly for VQE, the variational quantum eigensolver. That's huge in quantum chemistry, finding the lowest energy state of molecules. VQE's success hinges on its ansatz, its quantum circuit model, being able to generate the right kind and amount of entanglement. Because molecular ground states are often highly entangled, this has led to designing special entanglement-informed or entanglement variational and ansatz just for these problems.
Okay, so we've seen entanglement powering kernels, acting as trainable synapses, enabling new classifiers, and driving optimization. It's clearly a powerful tool. But you mentioned a duality. Here's where it gets tricky, right? What happens when this amazing resource turns into a liability?
Exactly. This is the double-edged sword. The very things that make entanglement powerful also make it, well, fragile and difficult to manage.
So what are the biggest hurdles when we try to actually harness this for practical machine learning? What trips us up?
Probably the most discussed theoretical challenge right now is this entanglement trainability paradox, and specifically the problem of Barren plateaus.
Barren plateaus. Sounds bleak.
It can be. Imagine you're training your quantum model and trying to adjust its parameters to minimize some error, some cost function. A Barren plateau is a region in that parameter space where the gradient, the direction you need to adjust the parameters, becomes vanishingly small, like exponentially small, as you add more qubits.
So the optimizer just gets lost. It doesn't know which way to go.
Precisely. It effectively blinds the optimization algorithm. Training just stalls. And a primary culprit: too much unstructured entanglement. If your quantum circuit is too deep or has too many random connections, it can act like what's called a unitary 2 design. It scrambles the quantum information too effectively.
Scrambles it, like noise.
Sort of. It spreads the information out so non-locally across all the qubits that when you try to measure just a part of the system, or when information gets lost in the hidden layers of a QNN, the signal you need for training just washes out. If you have this volume law entanglement, where entanglement scales with the system size between the parts you see and the hidden parts, the visible part starts to look almost random. Information is lost. So here's a paradox. You need entanglement for the model to be powerful, expressive. But too much, or the wrong structure of entanglement, makes it untrainable. Studies even show a negative correlation. More entanglement often means more barren plateaus.
Wow, so you build this incredibly powerful quantum network, potentially capable of amazing things, but it can just tie itself in knots and become impossible to train, like an engine that's too powerful to control.
That's a really good analogy. It's exactly that challenge. So navigating this isn't about just piling on more entanglement. It's about controlling it, managing an entanglement budget, if you will.
Okay, so how do researchers actually do that? How do you tame the entanglement beast?
There are several key strategies emerging. One big one is structured and problem-specific ansatz design. Moving away from generic, potentially scrambling circuits towards designs that reflect the problem's symmetries, like in VQE for molecules, or using circuits inspired by tensor networks, things like QMPS or QTTN, which inherently limit entanglement growth in a structured way. These tend to avoid the exponential gradient decay.
So tailoring the circuit to the problem helps control the entanglement.
Exactly. Another tactic is using local cost functions. If your measure of success, the cost function, only depends on a small number of nearby qubits, the gradients for parameters acting locally tend to stay large enough to train. It avoids that global scrambling effect. Control of circuit topology is also key. Finding that Goldilocks zone, not too connected, not too sparse, research suggests maybe a high number of connections, but mostly between nearby qubits, can offer both good entanglement and trainability. And there's even dynamic entanglement control, using helper qubits to sort of steer the circuit's behavior during training, pushing it away from those barren plateau-prone 2 designs.
Clever. But these are mostly about the circuit design and training. What about the physical reality? Quantum states are fragile, right?
Absolutely. That brings us to the huge practical challenge: noise and decoherence. Entangled states are incredibly delicate. Any interaction with the environment, thermal noise, stray fields can destroy the quantum correlations. Maintaining coherence long enough to compute is a massive hardware hurdle.
The environment is always trying to mess things up.
Always. But here's a fascinating symbiotic relationship developing. Classical machine learning is actually becoming a vital tool to fight these quantum problems.
Oh, really? How so?
Well, ML models are being used for noise-resilient entanglement detection. For instance, techniques like SVMs can help classify if a state is truly entangled even when the measurements are noisy, like one method, ROEW, that works even with over 10% measurement errors. ML is also crucial for quantum error mitigation and correction, QEC. Machine learning can help characterize the specific noise affecting a quantum chip, allowing for smarter circuit compilation or better design of QEC codes, which are essential for building fault-tolerant machines eventually.
That's amazing, using classical AI to bootstrap quantum AI in a way. So with all these challenges, but also these clever strategies, this raises the big question. We've talked theory, algorithms, problems. But are we actually building these things? Are they working? What does this look like in the lab, or maybe even edging towards the real world?
Yeah, absolutely. It's definitely moving beyond just blackboard theory. We are seeing tangible experimental demonstrations and early applications across different quantum hardware platforms.
Okay, like what? Where are we seeing entanglement make a difference?
Well, let's look at a few platforms. In photonic systems, using light particles, they've done that first experimental demo of entanglement-based classification I mentioned for vectors of different dimensions. They've also shown entanglement-enhanced covert sensing getting that 46.5% error reduction. Pretty significant. And really interestingly, an ML algorithm actually discovered a better way to do entanglement swapping in photons, which experimentalists then built and confirmed, so ML helping design quantum experiments.
That's meta. What about other types of qubits?
With trapped ions, there were early demos showing entanglement beating standard quantum limits in measurement precision. More recently, IonQ's area machine showed a quantum learning advantage on a tricky, non-local task that was robust to noise, needing constant resources where classical methods scaled up.
Okay, ions.
Yeah.
What else?
We see progress with nitrogen vacancy and V centers in Diamond 2. They've used the electron and nuclear spin entanglement for quantum-enhanced classification, handling multiple reference points per class. And on superconducting qubits, like those from Google or IBM, they have experimentally verified that quantum no-free lunch theorem showing entanglement being traded for data. They've also measured how entanglement entropy grows, seeing the shift from volume law to area law, which is super important for understanding and avoiding Barren plateaus in VQCs.
So across different hardware types, we're seeing these entanglement principles being tested and verified. That's crucial. What about specific application areas?
Yeah, and that's where it gets really exciting. A major focus is molecular simulation, drug discovery, and materials science. Simulating electrons in molecules. That's exponentially hard for classical computers.
Right, the infamous scaling problem.
Exactly. QML, especially VQE, offers a potential way around that by directly working with the entangled quantum states of electrons. So in drug discovery, people are using it to predict molecular properties, maybe even generate new drug candidates, or calculate binding energies accurately using VQE. There's work showing potentially reduced quantum resources needed to simulate relevant drugs like ibrutinib.
It could be huge for medicine down the line.
Definitely. And similarly, in materials, science accelerating the discovery of new materials, getting better predictions of electronic properties like conductivity or magnetism. Entanglement-enhanced measurements can also help characterize materials better.
Okay, chemistry and materials. Any other areas starting to see traction?
We're seeing emerging applications elsewhere, too. Fintech is one. QML models like VQCs and QSVMs have shown promise in areas like fraud detection, sometimes outperforming classical methods, potentially with lower latency. Also, secure communication and sensing. That entanglement-enhanced covert sensing is one example. And there are entanglement-assisted quantum error correction codes, EAQEC codes, which use pre-shared entanglement to help transmit quantum information more reliably over noisy channels. That's key for a future quantum internet.
Okay, it's really clear this isn't just lab curiosity anymore. We're seeing these concrete examples, maybe not universal speedups yet, but specific places where controlled entanglement gives a real, tangible edge in accuracy or handling noise or needing less data. It's not just hype.
Exactly. And I think this deep dive really highlights that. It's a field with just immense promise, but it's also navigating some really formidable challenges. If we try to synthesize all this, yes, entanglement is absolutely a key resource for quantum advantage in QML. It gives us access to those huge Hilbert spaces. It boosts expressivity, lets us potentially trade for sample complexity via the quantum NFL theorem. And these aren't just theories. Experiments are backing them up. But the big challenges are real. Barren plateaus from too much unstructured entanglement can stop training dead. Decoherence makes these states incredibly fragile. So the quantum advantage we're seeing today tends to be empirical. It's problem dependent. It shows up as better accuracy sometimes, or better generalization from limited data, or maybe lower error rates in specific tasks. It's not yet that universal exponential speedup people might dream of.
Right, it's more nuanced.
Very nuanced. And, there's still some debate about whether entanglement is always absolutely essential for every kind of quantum advantage. Other quantum features might play a role too, even with simpler separable states in some cases.
So, given this balance, the huge promise but also these tough hurdles, what does the road ahead look like? Where does research need to focus?
I think there are a few key directions. In algorithm and theory, we desperately need better optimization techniques that are entanglement-aware, specifically designed for these tricky VQC landscapes. We also need to move beyond just how much entanglement towards a real theory of useful entanglement. What kind of entanglement structure actually helps learning versus what hinders it. And critically, more rigorous proofs identifying where QML has a provable advantage, especially in sample complexity, are needed to really define its niche.
So better theory, better optimizers.
Sure.
What about the hardware and software side?
Big focus there on hardware and software code design, really optimizing the circuit's entanglement structure together with the physical layout of the qubits on the chip. Maximize useful entanglement, minimize noise. We need to keep pushing that virtuous cycle, using ML aggressively to characterize noise, mitigate errors in real time, verify entanglement, and of course, better software frameworks are needed to simulate, build, and deploy these complex, noise-aware, entanglement-structured models.
And looking even further out, any new frontiers?
Definitely. Exploring that non-entangling paradigm more is important. Where is entanglement truly indispensable versus just helpful? And a huge one. Bridging to real-world data. Developing efficient ways to encode messy real-world data onto quantum computers and creating algorithms that are robust not just to quantum noise, but also to imperfect data and hardware.
So let's bring it all home. For you listening, what's the big takeaway here? It feels like the future of quantum machine learning isn't just about building bigger quantum computers, is it? It's more about mastering this really delicate art. The art of controlling and structuring entanglement inside them. It's less about brute force, more about precision sculpting.
That's perfectly put. The key really is navigating that incredibly fine line between the expressive power entanglement offers and the practical need for trainability. The real revolution, I think, won't just be in having entanglement, but in learning how to precisely sculpt it for specific tasks. And maybe the provocative thought is, what fascinating new problems, what challenges we haven't even thought of yet, will this precise sculpting of quantum correlations allow us to solve next?